The purpose of today is basically just to restart the seminar and to say something about the research agenda over the next 6 months coming out of the summit and the primer, which has sort of led to some interesting new questions and a bit of a change in emphasis perhaps for some of us. So I'll talk about open problems a little bit, but I want to start by just setting the scene because I don't want to presume that everybody here sort of watched all the primer lectures and was sort of either at the workshop in Berkeley or sort of knows what went on there. So some history. So from June 19th to the 24th, we ran the first iteration of the primer. This will happen again at some point. Why? There we go. Okay. Some lag. So this was a series of introductory lectures covering SLT, mechanistic interpretability, alignment, and physics. This was in person in Berkeley and hosted by the Topos Institute. So thanks to Xiaowei Lin for being the point man on our ability to do that in person. The videos for that are on YouTube. If you go to devinterp.com/2023, you'll find the videos. I'll post the notes, which have all the links in them on the Discord. One of the highlights of that, if you haven't seen it, was Watanabe's lecture, which was a real treat. For various reasons, but in particular because he clearly thought rather deeply about the connection to alignment and the need for mathematics and alignment, and why this will be an interesting source of mathematical problems. So the week after that was the workshop, the summit. So that was from the 26th to the 1st of July. So that was organized by Alexander Oldenziel, Jesse Hoogland, and Stan van Wingerden. I think Jesse is here. I think Alexander and Stan are not. So that was on the topic of SLT and alignment, and specifically about developmental interpretability, which I'll remind you about in a moment. So that went very well, I think. Many of you were there, so thanks for coming. I think we all met each other. That was good in and of itself. And coming out of that, I think there's a renewed energy in SLT research and some interesting new ideas for directions, not least because of some of the lectures that took place over that week. So Colleen Lazaroyo gave some great lectures on physics. I'll say a bit about the research projects coming out of that in a moment. But I'll start by saying something about just the general way to think about this connection between SLT and alignment, because this is the SLT seminar, not the sort of alignment/SLT seminar. I think it actually does deserve a bit of discussion, the degree to which the seminar isn't now pivoting to be about applications necessarily, right? So if I'm to take off the, SLT is for applications in alignment hat and just put on my grumpy pure mathematician hat, why should anybody care about this particular connection, or indeed any connections to more applied things? And the reason for that, from a purely mathematical point of view, putting aside the application being very important, which I believe it is, it's my contention that as applications of SLT to interpretability and alignment grow, as I believe they will, this will lead to new and interesting problems. in pure and applied math. So not everybody working on SLT needs to care about alignment in order to find these problems interesting. And that's, I think, an important thing to say. It's not that these problems that we're going to discuss, some of the open problems, are only worth working on because you think the application is important. They're intrinsically interesting, and I think that's worth noting. Okay. Actually, this topic of SLT and alignment has been discussed a few different places over the previous 6 months, and I'll just quickly flag what those are. There was a couple of seminars here. There was SLT and Alignment Part 1, which covered some examples of interpretability over the course of deep learning history. There was these you can find on the metauni page. There was Part 2, which was kind of a sketch of an alignment plan, which developed over the course of the intervening couple of months into what was presented in SLT High 4 and the plan, which was the last lecture of the primer week. And I hope you've all seen the less wrong post that just came out, which was kind of the final form of that for now, which is towards developmental interpretability. And if you're at the in-person summit, you will have heard plenty about the thinking around that. So I'm going to assume basic familiarity with that agenda and just sort of say that at a high level, this application motivates the study of the following kinds of phenomena in learning machines. Detecting and classifying phase transitions over the course of training. And then attempting to integrate this understanding into some understanding of the final computation that's encoded in the model. We don't know how to do that, right? This is a research agenda. We have some ideas for how to detect and classify phase transitions, and I'll say sort of what those are in a moment. The second part is more speculative and sort of has been carried out, maybe you could argue, in toy models of superposition in some sort of very hands-on way. But this is the idea, this is where we're going. Which hat is the rainbow wizard hat? Yeah, that's a good question. I think alignment is not intrinsically a happy subject, so I'm going to go with pure math, but maybe you can disagree. Okay. So the main point I want to make today is that the principal bottleneck when it comes to this research agenda is not theory. Well, it's not that we don't need more theory, we do, and it's not that theory is irrelevant to this problem. It's certainly relevant, but we have some theory already in terms of phases and phase transitions and so on. What we're really lacking is mature tools. So in my opinion, the right focus over the next 6 months is not for everybody to, read all the proofs in the grey book and come up with some amazing new thing that we should measure in systems. It's to just get good at measuring the things we already know are relevant and measure them in a bunch of examples. This has the advantage of being much more accessible, and we can just start doing it right now. We already are doing it. Okay, so here's the priorities, therefore, in my view, at least in connection with this application. I'll say more about the kind of projects that are ongoing in theory in a moment. But I do think the following is the sort of highest priority when it comes to this application to developmental interpretability of SLT. So first, we need to develop scalable estimates of lambda hat. And is it actually a nu or a v in the grey book? I'm never quite sure. So this is the RLCT, and this is the singular fluctuation. We didn't talk really at all about the singular fluctuation in the primer. I think Edmund probably mentioned it in SLT Low 2, if I recall correctly. Edmund, is that correct?
Low 2. I don't recall, actually. I don't think I mentioned it at all.
Yeah, right. I mean, maybe it came up in passing somewhere or other, but...
Yeah, maybe in one of the questions. And
that's right, yeah.
Okay.
Yeah, so it's. I think it got mentioned in connection with the difference between Bayesian generalization and Gibbs generalization error and a few things like that. But we didn't talk much about it. Mostly that's because we don't understand it. I mean, we know the definition. We know how to measure it. But it isn't sort of as easy to understand, perhaps, as the RLCT, or at least we haven't paid as much attention to it. That is an oversight. So that the fact it wasn't mentioned in the primer and the workshop too much is a reflection of that emphasis, which is also historically there's been a lot more emphasis in SLT on the RLCT. That doesn't mean the singular fluctuation isn't important. As to their relative importance, I don't know that it really makes sense to talk about that. I don't have an opinion. But I think both are important when it comes to understanding phase transitions, detecting them, and to classify a phase transition has a technical meaning. Nu. Yeah, thanks, Jesse. To classify a phase transition has a specific technical meaning in physics, which is to find out which universality class it is, or which elementary catastrophe it is, or what the singularity that governs it is. We don't really expect to do that precisely in applications of SLT, but figuring out like some kind of approximate version of that precise definition is what I mean by classifying. That's to acquire a precise meaning later. Okay, to come back to the priority here. So developing scalable estimates of the RLCT and singular fluctuation seems to be the first step. So Edmund is working on a paper that's going to lay out our current understanding of doing both of these. You can also see his lectures for the lambda hat part. And that was something that was discussed and various groups were working on at the summit. Yeah, I want to just repeat something that came up in conversations with Edmund last week, which was that this is a hard problem. And it's not going to be one paper. So there is a literature, of course, estimating RLCTs using Markov chain Monte Carlo. At some point, maybe we should have more seminars about the various papers that are in that literature and the examples where it works and why it, why different approaches might be better. But I do want to emphasize the word scalable here. So the aim is not to have ways of estimating the RLCT which are very accurate in the sense that if we actually could compute theoretically the RLCTs, we'd match them up to 2 decimal places. We're looking for scalable estimates of something that kind of behave like RLCTs and singular fluctuations in the sense that We understand how both of those quantities play a role in phases and phase transitions, and we want something we can estimate which gives us information about phases and phase transitions in a way that the theory would suggest is meaningful. So the aim would be, Edmund can correct me if I'm wrong, but in the paper that he's preparing, to look at SGLD-based estimates and show whether or not they're reasonable in small examples where we know the correct answers either theoretically or we can compute them with MCMC as a justification for using these methods in larger examples. Would you add to that, Edmund? Is that accurate, or?
Yeah, I think that's accurate, with perhaps one caveat is that even in small toy examples where we know the answer or MCMC does work well, we don't expect the SGLD to exactly reproduce, like to give us the RLCT estimate. This is more kind of getting something that behaves qualitatively similar to RLCT than it being the RLCT itself, I think.
Yeah. So by qualitative similarity, we might mean things like ordinality. So if you have two phases and the true RLCT of one is lower, then you would hope that this lambda hat is lower. So phase sensitivity. So depending how you define lambda hat, you might expect it to diverge at a phase transition. For some definitions, it probably should, and for others, maybe it won't. But anyway, something will happen at a phase transition for the true RLCT and for any estimates of it, and you might hope that the scalable thing has a similar behavior to the true thing. And similarly for the singular fluctuation. I'll show you a couple of plots later from the toy models superposition, just sort of as a rough hint at how both of these things behave in that example. Okay, so the first thing is to so we have the definitions of these things. We have some idea of how to measure them in a way that might be scalable. Putting some foundations under that is the first priority. And then once we have the preliminary version of both of those tools, I think the important thing to do is to point them at everything we can. Right, so we just go mad measuring them in lots of different cases. Yeah, that's an interesting question, Matt. Seems like a good idea, right? Because we don't actually know how good those are. I guess probably we measure them. I mean, suppose there were proxies like that and we measure them and they always line up with the RLCT estimates, then sure, we'd probably want to use the cheaper thing. So that does seem important, yeah.
Or do the same thing to those measure on cases where we know the RLCTs and see whether or not they behave qualitatively like them.
Yeah, so either we end up with a cheap measure of something that's very important, or we disprove a lot of nonsense folklore. Okay, some examples of things that we might want to, except prank. Prank is obviously not nonsense folklore. We'll come back to that. So examples of things we might want to point these tools at. Well, we've discussed a bunch. Come on, Matt. You have to defend your babies. Otherwise, who's going to stand up for them? I'll just list a few different examples of things that are just sort of obvious that we can Yeah, maybe it's worth saying that code exists for both of these things right now. It will undergo refinements, but it's not like one has to wait for the final word from Edmund before at least starting to put these things together, right? I don't know, Edmund, if you would advocate waiting or proceeding ahead with the current versions of the code, but it will take some time for people to hook these things up and get started anyway. For both, that's right, for RLCT and singular fluctuation, it's in the same library, if I understand correctly, Edmund. Not in the version I have on my computer, but I believe the version that exists in your repository has both.
Yes, but they exist in various form of generality.
Yes.
And various form of in memory and speed efficiency.
Right, yeah. Yeah, so it's a bit of a mess, which is what you expect from research. But this isn't like something that will happen in 6 months, right? This code exists. One can just start trying to point it at things or plan for doing that in the near term.
Or contact me.
Yeah, that's right, yeah. So these are all things that are interesting. Type B phase transitions that may or may not be related to grokking. There is a couple of papers that came up on the Discord that potentially are related to this. I have some speculations there in connection with symmetry and so on. Double descent, at least data double descent. I think other cases might take some more work to connect to these tools. Phase transitions, we've talked plenty about. Anywhere you see a phase transition, you can attempt to be measuring these two quantities nearby in steps or data set size. Toy models of superposition, you've already seen, we've discussed some of the RLCT estimates in that case. Singular fluctuation, not so much, although Edmund, Susan, and I have been talking about it. And I'll show you a couple of those plots in a moment. You will have heard, if you're at the summit, about the work that Edmund, Garrett Baker, and Quinton Pope are doing on mode connectivity and RLCT estimates in large language models. As far as I know, that project's still ongoing. I don't know if Garrett, Quinton are here, or Edmund, do you want to comment? Is that still active, or is that maybe waiting for somebody to reinvigorate it post-summit?
I just talked to Garrett this morning, and it is very much still ongoing. And thanks to Garrett and Quinton, they train more models. That project might be sort of the furthest flung application of SLT. So that it's a lot of steps between that theory and application. It's not easy to navigating. We are also moving towards looking at generalization rather than just the RLCT estimate, because generalization measure might be closer to the things we collect in practice than RLCT, which is a few steps removed. Yeah.
Okay, so I would like that by the end of this year, doing these kinds of RLCT and singular fluctuation estimates on many different kinds of models, from small ones to large ones, different modalities, looking at different kind of phenomena, basically feels normal in the way that generating a t-SNE plot feels normal. It's not normal right now, of course, but I think by the end of the year, it could seem pretty routine. Like any tool, there will be limits, right? We have to develop a tacit understanding of which hyperparameters to tune, and there'll be all sorts of, black magic to get it to work properly, perhaps, but that's par for the course. So we get good at doing this, and it becomes a kind of routine thing. On the back of that, developmental interpretability can get started, right? Because the idea there is that we want to use both of these tools as our initial things that we measure about phases and phase transitions. And we have to get good at doing both of those things in order for that to work. And then once it works, we can go further with the things we will measure and connect it to more mechanistic understanding, etc. But we need these tools to work first. And phase transitions are one of the things we should point these tools at as we're developing them. But we need to look at as many different kinds of examples as possible while we're getting to grips with these tools. At least that's my opinion. So I'm interested if in people's opinion on that, or how, for example, Matt's comment, other things that are relevant here.
During the summit, there was a brief conversation about, or a brief mention of the lottery ticket hypothesis. I wonder if you think that and maybe just that lottery ticket hypothesis is another thing to kind of look at from this angle.
I guess that makes sense. I guess I don't know exactly how that's going to benefit from these measurements, but the lottery ticket hypothesis is one of the things I've flagged for a seminar talk soon. I guess it's a blind spot for me because whenever I hear people talking about it, I feel like they don't make any sense. So I have avoided it, but that's needs to change because it's clearly relevant to a lot of the things we're saying. And so I want to understand this better. So I would like either somebody to volunteer to give a talk on that, or I will give a talk on that, hopefully, in the next 2 or 3 weeks. But maybe it also makes sense to measure these quantities in those cases. Do you see how it's connected? Because it's not obvious to me.
Yeah, sorry, that's a good point. I don't immediately see how it fits into this category of with these tools, but it's just like another phenomenon that we should try and think about an SLT-based understanding of, or a dev interp kind of perspective on, especially because it was, I remember the way you mentioned it was like, it's another kind of failure mode for dev interp if structure is like already there from the start and is just progressively uncovered during training, then we don't gain any leverage interpreting it based on waiting for it to kind of be progressively accumulated in little pieces, because it's sort of already fully formed and just buried from the start. So I'm just thinking it maybe doesn't fit under this list, but under a different list somewhere.
Yep. It is on a couple of other lists of things to pay attention to, but I think one doesn't have to go all the way to lottery tickets this particular hypothesis to ask this question, because there are plenty of examples where we see learning curves that stuff seems to be acquired fairly slowly. So just forming a general taxonomy of examples of structure that do and do not form suddenly has a lot of overlap with what you just said, but is broadly important. And the lottery ticket sort of fits into that as one particular hypothesis of why structure might form gradually rather than suddenly.
Yeah. One other connection is to pruning. So, and pruning is connected to like effective dimensionality, I guess. So the lottery ticket is sort of saying something like you can maybe get away with pruning a lot of the network, although that's not necessarily the emphasis of the hypothesis or the phenomenon. But pruning is then related to, if you don't need those neurons or those weights, then maybe you are dealing with a lower effective dimensionality. And effective dimensionality, like I mentioned before in the chat, could be another observable that we could try and see what is the relationship between that and the RLCT.
Mm-hmm. Yeah, agreed. Okay, any other comments people want to make? So I'll just briefly give you the rundown of what I'm going to do for the rest of the time. So after we've had whatever conversation we're having now, I'll say maybe 10, 15 minutes about what singular fluctuation is. I'll show you some plots to sort of give you some idea of why it's sort of just clear looking at graphs that it might say something. about phase transitions. Partly that's just a kind of oversight in the way we structured the primer and the workshop to not have presented that information. And it's sort of relevant to, for example, if you go and read the Towards Developmental Interpretability post, you'll see there that we say that, similar to what I've just said, that our aim is to measure RLCT and singular fluctuation as our sort of two key measurable quantities that let us maybe get a window into phases and phase transitions. And we've said something about why the RLCT is relevant to that, but it isn't clear, I think, from the definition or anything we've said why we believe that singular fluctuation is a relevant quantity in connection with phase transitions. So it's also not that I have a deep understanding of that. As I said, the singular fluctuation is somewhat mysterious, but at least at it's sort of obvious that it's reasonable to expect that, and I would like to explain briefly why. Okay, but are there any more comments before we do that? And then I'll talk about ongoing projects and invite people to identify things they're working on if I miss anything. But yeah, any further comments?
I think this is missing maybe. Sorry.
Thanks. Sorry, I wanted to ask a question about the DevInterp agenda, but maybe we could talk about it later. I don't know. But when reading the Less Wrong post, there's kind of and hearing you guys talk about it, it's kind of like it seems to me there's like two kind of pillars to this agenda, which is something like the idea of developmental interpretability proper, which is that you should do interpretability over training rather than just at the end, and you should care about things like phase transitions and stuff like that. And then there's SLT, which is like a particular framework for it predicts phase transitions in the Bayesian case because of the sort of singular statistical sort of structure of the model class that we're dealing with. But do you think it's worth thinking about developmental interpretability separately from singular learning theory and these phase transitions, or are they like inherently linked? I mean, I wonder do you imagine that there's any version of developmental interpretability without singular learning theory, without RLCT and the singular fluctuation?
Oh, I think that's certainly possible. Yeah, I think that's right. Of course, the developmental interpretability, as we're talking about, it sort of grew out, of this process of asking how might SLT be relevant. But potentially, you could have a very successful theory of developmental interpretability, which sort of ends up not using SLT in a deep way or somewhere in between. I mean, it could use it not at all because maybe somehow RLCT and singular fluctuation and anything else that SLT comes up with just seems to not really turn out to be useful. Or it could be a bit useful, but something else turns out to be critical. Or it could be that the connections run very deep. Of course, it's uncertain. So what's being laid out in that post is, I think, a view on the different possible outcomes along that continuum. So starting with, I think it's hard to imagine that RLCT and singular fluctuation won't play a significant role in understanding phase transitions because those are the quantities that are sort of there. So I would be surprised if those don't become kind of standard tools in connection with this. What's more speculative is the deeper connections to the structure of phases and the geometry and all of that. I also feel that that's pretty reasonable. But yeah, it might be that, automated circuit discovery and some other techniques or something just turn out to be much more useful in practice.
The parallel being that it's somewhat like what catastrophe theory is to developmental biology, right? So I guess biologists has developed a lot of top-down tools, like directly working with organisms and quantities and measures. That's not sort of theoretical, but sort of directly working with cells. And they could be a lot of tools directly working with a model that is not sort of model in the abstract, but an actual neural network that could detect phases and structures that is different from what sort of theory could predict, I think.
Mm-hmm. Yeah, I think that's a good example.
There's something else to say. Yeah, right. This builds on the developmental biology point. To the extent that we expect a developmental perspective to work, sort of depends on it narrowing the search space and reducing the problem. And that's what you get if development consists of many different phase transitions. If everything evolves very smoothly and continuously, maybe this perspective actually doesn't make things much easier for us.
Yeah, but I think Matt's sort of asking, maybe the hypothesis of developmental interpretability is true, so that significant structure appears in phase transitions, etc., but that it turns out that understanding the structure that emerges in those phase transitions and how it fits together over training doesn't really need SLT. Maybe it's just quite straightforward. That could be true, but I don't have any basis for believing it's true. I suppose my current state of mind is something like, I feel that developmental interpretability, as we've stated it, is not necessarily true, but a pretty reasonable hypothesis for a research program. And the reason I feel that confidence is because of all the connections at which, part of which SLT plays an important role in bridging these systems to other parts of mathematics and physics. And without that, I feel like it would just be kind of guessing or like hoping that things are nice. So, that's kind of how I think about it. But of course, that doesn't necessarily mean that it turns out to be pivotal. Yeah, we'll just have to see.
I wanted to add one item to the list that builds very much on what I was just saying. But there's an observational approach here where you throw these tools at just checkpoints of various models where we don't know if there are phase transitions yet, and we just want to see if something shows up.
Yeah, I think that's right. Yeah, I guess my actual expectation is that we'll point these tools at lots of things like checkpoints and just find many phase transitions that are otherwise hidden. That would be kind of a good selling point for these tools, right?
Is there there was this concept of like a progress measure? Maybe this is covered by grokking and some of the other things on the list. But there was these, but I wonder if that's worth adding sort of explicitly to the list to see if these observables and so on are good hidden progress measures that when the loss isn't changing, something is changing in the structure. Maybe that's just what it means when you want to observe training.
No, I don't think. I think these are separate things. And to be blunt, I don't think the notion of progress measure really makes sense. I think it's something that maybe exists in some particular examples for very specific reasons, but I do not understand any general argument for why, like the hypothesis that you see a plateau and like secretly there's something happening and you can go and measure it. Like, I mean, that's, yeah, I mean, it's kind of related to the microscopic story, like in the toy models of superposition with the dynamical system that I'm writing down there. You can see there's a kind of progress measure, but I don't actually see why this is a general notion. So I don't really expect the RLCT and singular fluctuation probably don't indicate like continuous progress that otherwise looks like a plateau. I don't really expect that.
Well, another thing about the progress measures is it's informed by like the structure you know to be there at the end of training. So that's a very different perspective to what we're taking.
Yeah,
Just trying to discuss.
Clearly in the examples, that's how it's constructed. I suppose you might hope for some kind of generic progress measure that could be like defined somehow without knowing these specific details. I don't really know why you would believe such a thing exists. I mean, I like those papers, and I think that would be interesting. But I wouldn't, on my current understanding, draw any particular connection between progress measures and the things we're talking about, as far as I can see. Okay, singular fluctuation then, unless somebody wants to make further comments. All right. I think I'll save these boards for the open problems a bit later. So we're going to move over and then come back. All right. So I'm not going to give the actual definition because it's like, I don't know, you have to be kind of in the weeds a bit with the foundations to follow all the business with root T, A, X, U, and so on. But it's easy enough to understand sort of the quantity V, which is what you actually measure and which in a certain limit is the singular fluctuation. So that's what I'm going to focus on. So consider a neural network with weights W, inputs X, and the usual setup. So triple PQ phi. Okay, so I'm going to introduce the empirical variance with respect to the posterior of basically the mean squared error. And this is kind of what the singular fluctuation is talking about. Okay, so inputs X, outputs Y. Let's suppose we have some samples. Xi, Yi. Then we all know this calculation. C is like log 2 pi. Okay, so we can view this as a random variable. Well, there's two sources, you could say, of randomness here. So I'm going to fix the data sample, just view that as some vectors, and think about this as a random variable in W, with W sampled from the posterior. Now you say, what's the relationship between the data set dn and this particular data sample? Well, it will be one of the things in dn, but I don't want you to think about that for now. Just we have an input, we have an output, and with those fixed, we can consider this as depending on a w that's sampled from some posterior. Okay? So now imagine varying W, so varying the network weights. Well, then this mean squared error on this particular data point is going to vary. Because different networks will do a better or worse job of fitting to that particular data point. Okay, so that's a number, the mean squared error, varying with W, and we can ask for, well, the mean of that random variable, and we can ask for its variance. It's the variance we're interested in right now, so I'm going to let Ri denote this quantity. Oh, seems it was fixed. Okay, so what is that variance? Well, let's just compute it. So EW means expectation with respect to the posterior. Point of doing this is just to note that the log QXI term and the plus C cancel. So this works out to, you can take out this minus a half. I don't know that I wrote down the page from the grey book this is from, but you'll find a discussion of this, I think, in section 6.10. Not what I'm writing here, but the singular fluctuation. Now I need to be careful to get the squares and the brackets in the right place. Okay, let's see. Is the bracketing correct? I think so. Okay, so that's 1/4 the variance with respect to the posterior of the mean squared error associated to this particular data point. Okay. So now we can define the empirical variance. This is V. It's given a data set Vn, a Dn is Vn. So I'm just going to add the variances with respect to these, with respect to the posterior for Dn of all these terms. So these things I just computed. Okay. And I want to flag here that the data set appears in several different ways, right? So the data set Dn determines the posterior over which we're taking this variance, and it also determines these yi's and xi's. Okay, are there any questions about the definition? Next, I'll state the main theorem, which so far there's no singular fluctuation, right? So it's just some quantity. Note that we can compute this from a data set if we can sample from the posterior. So given a way of approximating samples from the posterior, like Markov chain Monte Carlo or SGLD, we can actually compute this quantity.
I think not a question, but a comment. So if anyone is reading the green book, this is called the empirical variance here. It's called the functional variance.
Right, yes.
And due to and there is a factor of 1 on n, so it's an average over data thing. So slightly different between the two books. And I think the nomenclature there is motivated by the last line in that board that Dan wrote, which is that it is the variance of what the neural network look like if you draw the network weight from the posterior.
Yeah, I think I like the Green Book terminology better. It is to emphasize that it's to do with the function is right, and also it's kind of weird that there's not a 1 on n here. So yeah, I find that yes. Okay, so here's the theorem. This is main theorem 3, I think, maybe. This is section 6.10. So I won't get into, I mean, the singular fluctuation plays a really fundamental role in the main theorems in a way that didn't sort of come up really in the primer. I don't really want to go into it too much now either, although ask if you're interested. But I'll just sort of state the main results. So these two theorems tell you sort of why this quantity is important theoretically, because it says that the empirical variance as n goes to infinity sort of gives you the difference between the theoretical and training generalization errors. So this is really important. Okay, so this says that the difference between the Gibbs and Bayes training errors and between the Gibbs and Bayes generalization errors are both governed by the singular fluctuation. And this this is the proof of Watanabe's equations of state. What I've written down, this is the theorem that gives the details of the statement there. But what's important for us right now is that the limit, if you take the expectation with respect to the data set of this Vn, that this limit exists. And yeah, just up to a scale, this limit is what is previously defined to be the singular fluctuation, but we could take it as the definition.
Is there any are there any bounds about how fast that convergence in probability has to go, or like knowledge about what determines that?
I do not know. I don't even not know how to bound it above, apart from this very complicated thing that's around the same place in the Grey Book.
But practically, it doesn't matter.
We don't know. Yeah, I mean, I don't even think we've done enough experiments to have even a sort of gut level answer to your question. I think it's an important question. We're just really quite ignorant. I don't know, Edmund, if you have more to say about that.
Yeah, I think not enough experiment and not enough understanding of the result in SLT beyond the free energy formula result in not having anything to say about this question. Yes, the rate of convergence and things like that. I think that's sort of part of the proof, and so I can say something. So the expectation, if you take the expectation of everything on the board, then the next order term. Okay, sorry, no, okay. Let me just not say anything. Sorry.
Yeah, I think it would be worthwhile having a seminar at some point on the singular fluctuation, and maybe saying what we can say, which probably fits nicely into
yeah.
one seminar. But yeah, I think this both theoretically and experimentally requires a lot more attention.
Yeah, the proof for a lot of these things is actually sort of the bulk of
That's right.
the proof in the gradebook. So I think it's worth a series of seminars going through main Formula 3.
Yeah, so it's a bit funny that at some level we haven't talked much about this because it's so critical to the actual details of the mathematics. But on the other hand, it's also like kind of hard to understand. So let's just be clear on what the singular fluctuation is. So the singular fluctuation, it's defined in terms of, you'll see in the book, you involve an inverse temperature. I'm just setting that to be 1. So it's this limit of this empirical variance, which is measuring how much the mean squared error, sort of how widely distributed that is around its mean. Okay, so let me give you an example of why this is potentially relevant to phase transitions, and then I'll show you some plots that show that this kind of rough expectation bears out, at least in some very limited, in some examples. We don't have a thorough understanding, but I think we could certainly by the end of this year have a pretty robust, sort of empirical feeling for how this quantity behaves, and I think we should. Okay, so let's imagine a first order phase transition of the kind that was discussed in SLT High 1. So here's L, here's 2 local minima, which I'm thinking of as 2 phases. They have various energies, and these are like the regions of parameter space which correspond to those phases. And I want you to consider these 2 phases as being in sort of competition. So that is, there is a non-trivial posterior mass in both phases. And I'm, as drawn, E1 is greater than E2, and lambda 1. Let's imagine that as being less than lambda 2, so there's actually a possibility of a phase transition. Okay, then I claim we expect Vn to be relatively large. Why? Well, by definition, Vn is the variance of the mean squared error over the posterior. And this, I mean, as soon as you're taking something to do with the posterior, and if the posterior mass is concentrated in these 2 places, then it's kind of talking about the value of the mean squared error in those 2 places. And the mean squared error in those 2 places is, roughly speaking, what the E's are talking about, right? So you've got these 2 energies, and they're separated. So that variance is going to be higher than it maybe would be if there was just a single phase that was affecting or contributing to the posterior. I don't claim to have any theorems about that, but that's kind of, I think, a reasonable way of thinking about the relation between the singular fluctuation and phases. Somebody should actually do some grown-up math and say something about the relation between singular fluctuation and phases. That's about all I have to say on it. But now I'll show you some plots, unless does anybody want to ask more about that or offer any further deeper commentary?
Is this, I can't remember, did you say, is this quantity like temperature dependent?
Yeah, the singular fluctuation is defined with an inverse temperature dependence. That's right. But it's kind of trivial. It's just, I mean, it just shows up as a scale factor on the right-hand side. I don't know that the dependence on beta.
I think it's based on the definition is very clear that so if your posterior is at a different temperature, is tempered with a different temperature, then the fluctuation will change, and that's the dependence.
Yeah,
So
that's right.
the higher the temperature, the larger things, the more far-flung ones will contribute.
Yeah, that was exactly why I asked. Thanks.
Okay, let me show you what this quantity looks like in a couple of examples. Okay, probably want to click on that. So this was, we showed at least the first of these plots in SLT High 4, I think. So this is toy models superposition, and it's showing the posterior concentration in a few different phases corresponding to different local minima of the toy model's potential, which are themselves, at least these ones, classified by certain polygons. So you can see here 3 gone, 4 gone, 5 gone, 6 gone. Below, you'll see a plot of estimates of this lambda hat. And then there's Vn, which was just defined. Or at least I believe that's what I just defined. Is there any gap there that's relevant?
The green book, yes. The green book version.
Yeah,
so the one on N version.
Yeah, right. Good. Okay. Yeah, maybe, okay, that's now quite confusing. So maybe I'll go back and change that. Well, or maybe I'll change this picture. So this is NVN, right? Sorry, no, 1 on NVN is not defined, as you said.
Yep.
Yes. Okay. So you can see, well, it's without things to compare to, I guess it's a little tricky to see what's relevant here.
Should that be capital N? And also in the subscript,
yeah.
right? So because here lowercase n is related to the features and so on.
Yeah, except this, yeah, okay. So this here is capital N. Capital N. That's right. Yeah, so capital N here means data set size. That's right.
So could I just interpret this in terms of what you said on the previous board? There's a point where the red line is like dominating the, that appears to be where the singular fluctuation, the functional variance estimate is low. So is that because it's like some kind of, there's posterior concentration there, whereas not elsewhere? Like somehow the posterior then spreads out more?
Yeah, I mean, my reading of this plot is that, and that's what I said on the previous board, right? So if you've got a mix of two phases, then the variance of the mean squared error over the posterior is relatively large.
Okay. I was kind of predicting what this plot would look like before you put it up, and it would be something like, as you move between phases, you see a spike in this because there's like a moment where you're sharing between the two phases, but then it's a phase transition. So relatively quickly you end up concentrated in the second phase, whereas previously you were concentrated in the first phase. So in between you're sharing and the variance goes up, but I don't really see spikes here. So is that
Yeah,
is
it's-
that prediction kind of flawed?
Well, in general, in these kinds of plots, you don't see extreme spikes if they sort of happen over a relatively short n interval. So it's, yeah, partly I think we just don't understand exactly how to answer these questions. It's sort of like I'm showing you plots and saying, look, something is going on there. It isn't clear exactly what we should expect to see for the singular fluctuation.
Okay.
I think these plots are also, I mean, the situation is also quite strange in that you have an extended range of n in which two phases coexist, which is why you get, well, it seems like, I'm guessing, why you see the empirical variance being relatively high for such a large range of n's, right? It sort of stays high there around 0.001. That's in cases where you just have a single phase dominate after some period, it does decrease. So this is kind of a bit of a freak situation. But the fact that the empirical variance goes down and then back up again, I think probably is robustly associated with the fact you have this coexistence of these two phases, the red and the green. Yeah.
Cool.
Behind all the sort of verbal terminology here is also the fact that this is we are using estimated k-gon to define phases, and those k-gons need not be k-gons. So for example, the red line down the extended number of n's dataset size where the 6-gon seems to be present could be a 6-gon that is almost a 5-gon, for example. Just pointing out that.
Yeah, I think that's important because it's worth keeping in mind. The first plot depends on us knowing something about the problem and the nature of phases, right? So to make these plots,
Yes.
we have to pick out some region of parameter space, and then we declare that to be a 5-gon and this to be a 6-gon, and that's not something that we can do in general. Whereas the second and third plot we can do in general, modulo our ability to actually scale these estimation procedures. So so we see these beautiful phase transitions in the first plot, but that's not something we expect to be able to do in general. Whereas looking at the signature of those transitions in the second and third plot is something we expect to do in general. So what we're aiming to do in these small examples is to be able to move from relying on the first plot to be able to rely on the second and third in terms of identifying phase transitions. And that is pretty obvious in these examples. I guess we're not showing you examples where there is no phase transition for you to compare with, but the fact that there's kind of multiple bends like this is typical of there being a phase transition, and this kind of kink is also typical. You can see in the second plot maybe, I guess it's broadly similar behavior, but it's much more complicated somehow. So you see the nature of this. The behavior down here is different. Maybe the third one is even a better example.
I wonder if that Vn has asymptote to the singular fluctuation.
Yeah, that's right. I mean, look at the Vn in this case. This is pretty interesting. So the third one here, m equals 2, n equals 8. This is a mess, right? And the mess is visible in the Vn. Somehow less visible in lambda hat. I'm not sure why. But you definitely can tell something's going on by looking at Vn here. I don't understand why or what it's saying, but so the point of these plots is not to claim we understand what's going on here. I think we will, with more work, understand better. That's like the theoretical part of the progress we want to make over the next 6 months, is being able to actually tell the story of these 3 plots and not just be waving our hands at things. But the point of showing these plots right now is to indicate sort of why we, besides believing that it's possible to estimate lambda hat and the singular fluctuation, why it seems pretty clear that these give you some insight into the into the nature of and to the existence of phase transitions. Okay, I think that's all I wanted to say about the singular fluctuation. Yeah, we should return to this topic both experimentally and theoretically. But yeah, ask more questions about that if you have them. After that, we'll talk more about the ongoing projects. Okay, seems no further questions. So let's move back over to the original set of boards.
I do have one question.
Oh yeah, go ahead.
You said that you prefer the name functional variance, but it's like just about the distance from the true function rather than, it's not about f, it's about the loss, like how far is f from y. Like, do you think that how do you think about that in the intuitive picture of the functional variance? And do you think that it would make sense to actually consider some kind of variance in function space as you vary w across the posterior? Like, how does f change? How does it move around?
Yeah, I'm not sure.
I guess this is something like that, actually, because...
Yeah, I guess that is how I think about it. Yeah, you're sort of saying, okay,
I think my confusion is because this is like a variance of a variance or something like that. Like, it's a variance of a distance from a mean.
Well, it's also the variance of the log density ratio, right? Which is the thing you integrate to get the KL divergence. So it's like, the way I think about it is the KL divergence is an integral over two things, right? It's an integral, the KL divergence is an integral over data, right? Over X. And it's a function of W. But there's sort of like the more fundamental quantity is the log density ratio, which is a function of both X and W, and you can kind of integrate it with respect to either. And this is kind of like the more fundamental quantity. And what we're talking about here is the variance of that quantity, that sort of density for the KL divergence over W. So that's the sense in which it's a functional variance, because that function, it's kind of like as a function of on X, like you sort of think about mapping from parameters to functions on X, and then you're kind of, I think that's how Watanabe is thinking about it. It's sort of like the variance of that random variable in function space, something like that.
Okay. So I'm just looking at the wrong function.
Maybe. I don't know. Edmund, would you agree with what I just said? Or I might have.
Yeah, I'm trying to formulate things in my mind, but like if you forget the y, not forget the y, but replace y. So if this is a realizable model, meaning there exists a W0, so replace y with f of x at the correct weight. And then if you forget about the fact that if there's only one data point, so you're not taking mean over data point, then you are taking the variance of the distance between like you say the function at W and the true one. And then if you kind of think of the posterior being as sort of inducing probability distribution on the function space, then that's kind of a function of that variance of that distance in function space. Okay.
Yeah.
Lots of hand waving, but
Yeah. Okay.
All right, shall we move back over? Oops. So I'm going to write up here the projects that I sort of know of that are ongoing and tell me if there are others I should add. But this is kind of, there's an open problems channel on the Discord for the summit, which is now the developmental interpretability Discord. So that's kind of maybe the canonical place that lists open problems. What I'm listing now are sort of the ones people are actually working on. A couple of which have already been mentioned. So I'll start with what I'm doing, which is you could classify the first two things as defending the shit that I've already said in SLT High 1 and SLT High 4. So the internal model selection story from there is correct, but actually publishing a paper with the proof requires actually dealing with a few technical issues. I don't really want to get into them here. I can say more if anybody cares, but there's some issue with the boundary. There's hypotheses in there about optimal parameters not being on the boundary. Xiaowei and I have been talking about it. I think it's can be removed, and that would be sort of actually important for some of the applications. Something I would really like somebody to think about more is actually checking relatively finite variance, this condition, in more examples. This we don't know how to do well. So this is me and Xiaowei. Yeah, I'll put sort of timeframes on these because I think it's useful for people to know. So I'm hoping we have something about this out September, October. And then there's the work on toy models of superposition, which is meant to ground a lot of this discussion in phases and phase transitions in SLT and the connection to phase transitions over training, at least in some simple examples. So this is kind of what you heard about in SLT High 4. So this is joint work of myself, Susan, Edmund, Zhongtian, and Jake Mendel. So this, I hope we're done with by September, because I think we should try and submit this to ICLR. We'll see how we go with that. Okay, the foundations of Lambda Hat and Nu Hat. That's the work that we just spoke about. Unless Edmund tells me otherwise, I think that's Susan and Edmund. And I think you guys are aiming at triple AI, is that right? That's in August.
Yes.
Silence. Yeah, silence from Edmund. August. That's so soon.
Yes.
Okay, there's the mode connectivity work. I won't repeat the names. That's, well, I won't write them. That's Garrett Baker, Quentin Pope, and Edmund. And I don't know what the time frame is on that. Maybe it's not clear. Yeah, since a few people were interested in this at the summit, so I mentioned there Riley Morris's work. So his master's thesis will be on some of the relations between differential linear logic, sort of structure there and structure of singularities. His thesis in principle won't appear until the middle of next year, but I think there will be something there to discuss by the end of this year, I hope. But that's kind of like a more long-term thing. And then there's the work that's coming out of what I'm doing with Colleen. This story with BVBRST. Yeah, who knows? This is sometime next year. This is hard. The point of that, if you recall, was to clarify a few things, but in particular the role of this subleading terms in the free energy formula and their geometric content, I think, should in part be sort of explained by that. But the first thing I'd like to get out of that is, again, in the situation of the toy models of superposition, to it's almost sort of there in Ed and Colleen's lectures, plus a little bit, but to relate Euclidean field theories, G-flow, and marginal deformations to the sort of situation that's being discussed in toy models of superposition. I think that will go some way to clarifying why it's reasonable to think that this picture with SLT might say something beyond just providing lambda and nu in the situation of developmental interpretability. So I'm putting Ben's name there, if that's okay with you, Ben. Thumbs up. Okay, good. Okay, that's all I had written down. I think we're going to try and get something on that out in late 2023, but we'll see. Okay, so that's what I'm working on, and what I know of as concrete projects. There's a lot of other stuff that's going to be going on in connection with developmental interpretability, looking at many more examples. That will generate papers, but I don't know if right now it's clear what exactly those would be on. So maybe, Jesse, if you know more particular things I should add here, tell me, and anybody else, if you sort of have in mind something specifically already you're working on, which should be added here.
Let me pull up my list 1 second.
Yeah. Zach, I don't know what the status of the stuff you were working on at the workshop was. Is it at a maturity level that would make sense to point at a particular, is it like leading to a paper yet, or is it more exploratory right now?
I think I have a thing I want to prove, which if I could do would make a nice paper, but I don't know if it's possible yet. So that's the current status, is working out different strategies for that, but I don't know where you would put that.
Well, that sounds at least as certain as many of the things on this list. So what was the thing you want to prove?
Yeah, it's kind of an extension almost of depth separation results, which I guess for people who aren't necessarily familiar, we have these results that characterize sort of, if you have tractable networks in the sense of like, you don't want to use exponentially many parameters or whatever, what the architecture has to sort of look like in relation to your problem. But what it doesn't currently say, which we would like it to be able to say, is something like tying the actual internal implementation to the problem structure. So being able to say like things about exactly, where, sub functions must be implemented, like they must be implemented in order, or like if the architecture looks like this, then there's so little degrees of freedom that like you can uniquely identify it or something like this. Yeah, this is the high level idea, and there's a couple proof strategies that I'm working on. That if anyone's interested, I can describe those more.
Cool.
So I can add 1 or 2 things.
Yep.
So on the experimental side, working on like an actual library, cleaning everything up, making sure it has a very clean API is well documented, that kind of thing. So that's not going to lead to a publication. It's something that other people can use.
And it seems
There
like,
was a project. Yeah.
well, I mean, it probably is reasonable for that to be also a publication if, I mean, once you have the library running things like the estimates of lambda and nu on it at some points in training or something is not much more on top of that. Is that
right? When with the examples, I'm just looking at.
Yeah.
Could you clarify, is it a library of examples like is it toy models, or is it like a library to do the RLCT estimation, or?
Yeah, both. That'll be the techniques that's what I'm starting with, and then compiling lots and lots of examples.
So it's an example of things with phase transitions, is that right?
Yeah, and then also, there's also a few systems we want to look at, like vision models, right? Where the structural formation just has not been studied to the best of my knowledge, which is crazy. So things like that.
Cool.
While we are adding things and sorry,
Edmund, you go first.
Related to perhaps this is I think Matt's earlier idea is worth noting, which is sort of exploring existing scalable technique out there that is not necessarily sort of singular geometry aware, but just evaluating them on a zoo or library of toy models, and where we know the correct answer and see whether or not they are good. Not sure this is kind of a paper thing, but might be sort of a good broad knowledge base kind of thing.
Yeah, I think that would be good to do. I think we should be pretty focused on actual publications, though, over the next 6 months to a year. I think it was, I think, reasonable. I mean, our work on SLT so far has not led to a lot in terms of outputs. That's to be expected because it's a difficult area. It took a long time to get our feet on the ground. But now that we see a few ways in which things can actually be cashed out in a way that could lead to publications, either in journals or in conferences, I think we need to take full advantage of that as rapidly as possible, because like right now we're in a position where actually this isn't a standard thing, right? There is low-hanging fruit once you know that you can estimate lambda and nu and that this might be related to things that matter. Going out and measuring this in lots of different places is like 10 to 15 easy papers that actually mean something. And somebody will write those papers, and it should be us. So I think for the in the near term, we should be pretty focused on doing that. There will always, of course, be other kinds of questions we can be asking, but I would suggest submission deadlines. Yeah, thanks. Yeah, this is not really like, I mean, I've published one paper in ICLR, and I don't know where the other one was, the IEEE something that Susan put our paper in. This is not my native territory, really. So there are probably other conferences I'm missing here, but these are some of the major ones. Those are the deadlines. So yeah, we should be aware of those. Okay. So regarding ongoing projects, CULT. Yeah, I don't know anything about CULT. What do they publish?
Computational Learning Theory, I think, is the name of the conference. I haven't published anything yet, but sometimes get mentioned alongside these things.
Right. Yeah. We can take a look. Yeah, so I think in terms of things that will be relatively easy to do if you have an ML background or are willing to do more coding, pointing lambda and nu estimation at some of the examples on that earlier list, I think is kind of a good thing to do. The mode connectivity work that's ongoing is an example of that. Yeah, lottery tickets might be another. I don't know. I mean, we should spend some time thinking about other things to point these tools at, because I'm sure we can come up with at least as many other things to add to this list as are already there. And those would be like my recommendations for low-hanging fruit at the current stage of things. Okay, I think that's all I wanted to say. But yeah, please comment now if you have things to add or questions.
Edmund and I are going to work on a literature review of all of the papers that exist so far that mention SLT and neural networks or RLCT estimation or all of that stuff.
Yeah, what happened to the prank work? Is that going to be a paper, or I mean, the stuff you guys were working on at the summit?
I think it's still too exploratory, but if we keep, I think Edmund might be still working on that. Is that the case, Edmund?
I was looking at it last week and it's stalled this week because of some other priorities. But yes, it's still exploratory is a good characterization. There are still things that we should sort of low-hanging thing we should push and see whether or not it works. Then we can see where to go from that.
I'd like to. Oh yeah. Also, I'm not sure if Rowan's here. Yeah, we were looking at using the kind of prank based algorithms to kind of count. What's it called, Rowan? The irreducible components or something like that.
Oh yeah, yeah.
Just more.
Yeah, that algorithm to generate the irreducible components of small models. I have actually been trying to work on that. I've been pretty busy this week, but it's on my radar.
Yeah. So I guess I would class this direction as something like to push the algorithms that we have, both sort of theoretically and in code, for having like a principled analysis of where we are in the parameter space in terms of are there functionally equivalent networks nearby, in case this turns out to be relevant for phases and it seems like it's related to RLCT maybe. It would be good to have tools to kind of very surgically tell us like exactly which directions we can move in to not vary the function and that kind of thing. And I think we're thinking about those algorithms.
Yeah, I think that's going to be increasingly important as we move past this first stage of like, okay, once we know what we're doing with the existing tools like Lambda and Nu, how do we invent and sort of measure more refined things about like exactly the kind of thing you just discussed. And yeah, Adrian's also thinking a bit about that. So yeah. Okay, so the next steps, we're going to, of course, be continuing this seminar. I put on the Discord some potential talks in the near term. A lot of those will be oriented around exactly the things at in item 2 of this list, like things that inform either developmental interpretability or just more broadly looking at measuring Lambda and Nu in examples. So yeah, if you're interested in working on something like that, then please, look at one of those and maybe give a talk. And yeah, I won't ask for volunteers now, unless somebody already knows something from there they want to speak about or something else. But we'll discuss that on the Discord over the next week. Okay. I think that's it. So thanks, everybody. And, so going forward, I think we'll try running the seminar. It's a 1.5 hour time slot. But I think from week to week, there will be research updates from each of us and, things we can learn from that. So I think maybe we'll run it as a 1 hour seminar and then a 30-minute kind of discussion. Maybe that's in small groups or somebody or other saying something they're working on or stuck on. So that'll be part of coordination of a broader research agenda. So that's the plan. Okay, any final comments? Jesse, is there anything you wanted to say?
Let's do this.
Yeah.